Hi everyone. I have the honor to announce the first live speaker of this event, which is my advisor Christian Blohmann. He's from the Max-Planck-Institut in Bonn, and he's going to talk about diffeological groupoids. Yeah, and I think that's all I'm supposed to say.
Okay, very good. Thank you very much. I'm really giddy to hold this like a physical piece of chalk and write on the board and to give the lecture to physical people. I haven't been doing this for almost 2 years now, so I hope I still know how this works. Let me first talk about the structure of this talk, what you can expect. And I realize there are many experts on many of the aspects of what I'm talking about, but this is supposed to be a mini course, so there's some pedagogic baseline requirements I think I have to adhere to, and so maybe some parts at the beginning may be boring to you, but I don't expect everyone to be an expert in B group. So the first part is going to be groups. So this will be a lightning round on groupoids, sorry. The lightning round on groupoids and groupoids, and then we get quickly to diffeological groupoids, interesting examples. So the second part, so this is not the 3 lectures. The second part is going to be the largest, and this is going to, the title is Differential Calculus. On elastic that's the word I need, that's the concept, that's the word I need to explain. Logical basis. That's the new technical ingredient for or a new theory. Points. I've written lecture notes for this, so you don't need to take notes if you don't feel like it, and I'm going to make them available via maybe a secret link that I'm going to send to Francesco. And they contain much more than what I can say. Okay. So lastly, let me mention a few names. I wouldn't be doing this if it weren't for 3 very bright students. So for Lori Kadian, a PhD student, who's going to give a talk on her PhD topic on Thursday. Then Annika. Who's done related things in her master thesis, and incoming master student. Okay, good. Yeah, I was really scared when I saw the slides of Alexander, because it was exactly the first part of my talk, perhaps a longer version. So I'm going to be really quick. So I should at least explain the words of the title. So let me remind you what a groupoid is very fast, and a Lie groupoid, and then start about examples. So okay, so a groupoid, so the quick definition is a category on the isomorphisms. So in that picture, you have some arrows. Let me draw them like this. With endpoints arrow G, endpoint X and Y, and an arrow H, Z. And you can compose. That's G times H. With another one. F can compose this way, and if you compose them all together, So that's G H. It's associative. That's all there's to be said. Well, if it's totally new to you, that won't help much, but that's all I'm going to say here. And I'm going to call the endpoint maps let's call the space or set in that case of arrows G1, and then it comes with two maps to the endpoints. So that G2, I'm calling the left and the right endpoint map to this set of objects G0. And you can decide whether you want to place the tip on the left or the right, because there's roughly 50% to do it one way, 50% to do it the other. But we all agree on what's left and right on the board. And that's a suggestion by Weinstein, would save the community a lot of headaches if you didn't decide where's the tip, where's the shaft. Okay, good. So what's the main examples? Because people usually, when they generalize from known concepts to groupoids, they have a specific class of examples in mind, and that informs their terminology and their concepts. So let me just remind you what I consider to be the three main examples. You may differ, you may disagree perhaps. So you have relations. So that's a subset, it's called relation itself G1, that's our arrows, a subset of pairs of that satisfying the usual properties is an example for groupoid. The endpoint maps are the projections. And you have exactly one arrow between any two, at most one arrow between any two objects here. Then you have, of course, groups. And you have group actions. So it's just a group acting on some kind of space. This is the left. This map is the left endpoint map that we call action groupoid. Depending on what you think of, you might call then a groupoid where there's an arrow between any two elements of the base. You might call this transitive or wide or maybe simple if you think of the group. That's what I mean by this informs often terminology and what you think of it. If you're thinking of equivalences, you may be maybe a stacked person. But that leads to differential, to stacks, combination of stacks. Okay, good. So now we add geometric structure. So if you were to define a topological groupoid, you could just define in the following way. Groupoid external to the category of topological spaces. And sometimes you can see this as a definition for a Lie groupoid. People say a Lie groupoid is a groupoid returning to smooth manifolds. That's not a good definition. And I'm insisting a bit on this because that's the kind of things we have to contend with when we go through the diffeological setting and really understand what we exactly need to have a good infinitesimal object for a groupoid, in the same way as we have it for Lie groupoids, then later for diffeological groupoids. Okay, so this is not a good definition for topological spaces with smooth manifolds. That always means finite dimensional and smooth, right? in this course. Why? So Why? That's the first issue. Well, the multiplication is defined. This multiplication. Sorry, I really have to relearn writing on blackboards. Multiplication is a map defined on composable errors with matching endpoints. And this pullback generally doesn't exist. And then people say, oh, that's why we need an additional quantity. We want this pullback to exist. And then they claim this is why we need submersion. That's not true. I can give you interesting and fun examples for all the pullbacks, also higher pullbacks exist. And still it's not what we want because there's the second issue. We want to be able to define a Lie algebroid in the way as we do it for Lie groups. So it's essentially take the set of invariant vector fields. And in order to have this, we need a right action. It's not on the entire tangent space in that case, but on vertical tangent spaces. And for this to exist and to be smooth, we need additional property. So have the concept of right invariant vector fields. And to be able to smoothly identify right invariant vector fields with sections of a vector bundle, that's the Lie algebroid, we need this and the higher sets of the nerve of composable errors. This be isomorphic to T. If this were supposed to be true for if I fix one and have an arbitrary space, this would be equivalent to this being a submersion. To the endpoint has to be subversion, but at any rate, both of these issues are fixed by assumption. That hence are subversions. Okay. So then we have the definition. You see there's also some trickery going on of some additional thoughts that you need to go through since the usual category of manifold is not convenient. So the things that go wrong if you just work in a categorical way naively. Okay, so so the definition is such that one manifolds are subversions and our structure maps and I deliberately put these kinds in this order because characteristics manifolds, then these are submersions, only then the thing on which the multiplication is defined even exists manifolds. Okay? And then you can require these matches. So this, be very careful. Maybe that's what the issues are about.
Are manifolds Hausdorff or not?
They don't need to be. Yeah, it probably shouldn't be to not exclude foliation, the groupoids associated to foliations. Not necessary at this point. Okay. And so here's the picture of a groupoid. Discussed with any lines here. Seen this. So, yeah. identity bisection T1 is some space, then you have the R fibers X, and you have the outer fibers. The point Y, and you have an element G and an element H. You have a geometric picture of the total thing. Okay, so examples. Things get already a bit more interesting due to the widening technology. Okay. Really forgot that we had to do this here in the physical world. It's actually fun. I'm really enjoying this. Okay. Examples for points. Well, first the groups. The points of a plane. For smooth actions, we have the action groups as before. Equal points are as before. Actions of group. Then here's already one interesting case: orbifolds. Maybe you know the sort of the chart definition. There's a clever definition in terms of groupoids, and this is a groupoid where the characteristic map, which is the map from T1 through both endpoints, is proper, and one of the, say, the right endpoint map is a local diffeomorphism. Another word for this, and so the slogan is proper vital groupoids are the same thing as orbifolds. Okay. Then an even more fancy object is differentiable stacks. So for ordinary stacks, they don't need to be groupoid, but for differentiable stacks, they're all presented by groupoid, or less by definition. And then the slogan is differentiable stacks are Lie groupoids up to Morita equivalence. And the precise statement is there's equivalence of two categories between stacks and Lie groupoids, Morita equivalences, and biprime groups. So here's another example that I haven't seen, and I don't mind seeing, and I don't think it's like entirely new, but I haven't seen a reference for this. So let H, let it be the group H and an H action on a manifold. And K, H, a closed subgroup E subgroup, okay, E subgroup, such that induced action use it to action A is free and proper. then we can take the original action groupoid and take a quotient by 2 copies of K. So the space we have is we take the left group quotient of H by K. This has still a right, H action. If this action is free proper, it's a principal bundle. So M is a principal bundle over the quotient. So I can write M, it's a principal bundle. Now I take the quotient, so it's the associate principal bundle to M with this as fiber. And this maps down to the action quotient. And this is what we call the reduced groupoid, or the reduced action groupoid. No, that's not what you should call it. The reduction of an action groupoid. Of an action groupoid, which is not itself, again, an action groupoid unless K was a normal subgroup to begin with, which is not an assumption. So this is a groupoid. I'm telling you this because action groupoids is an interesting starting point to construct new ones. You know, sometimes as a groupoid person, you're embarrassed to come up with good but explainable and tractable examples. I think this is a very good class. And I could tell you many interesting examples of this in field theory, for example. Classical field theory, general relativity, things like this appear, as we've realized. Okay, and then you can perhaps last example I could give is that since now you have differential structure, you can use that to construct new groupoids. So you have just applying the tangent functor. Now again, you need that L and R is a submersion. This wouldn't work if you just require the pullbacks to exist is a groupoid. Let's call the tangent functor. Similarly, we just say this word. Points. You have to watch out a bit when you define jet groupoid. For the first one, the J1 jet groupoid needs additional conditions, but all the higher ones you just apply the jet functor to that. Okay, good. So now we come to the actual topic of this workshop. Now we get to the bigger stuff. I won't really use the word infinite dimensional. Here I just can say perhaps not finite dimensional, okay? Because I actually don't have necessarily my stuff modeled even on vector space as something that has a dimension. So I'm just saying I'm leaving now, start to leave the finite dimensional manifold ground. So the first things that come to mind is groupoids that are modeled on some kind of function spaces. That's one you would have seen as a geometry, right? Okay. So maybe the first example you've seen in a different geometry course is the diffeomorphism group. And then someone somehow explained to you that the Lie algebra of that group is the Lie algebra of vector fields to sign. But usually they don't use the terms Frichet manifolds or something doing this in an introductory course. And they do some magic fiddling around with smooth families. And that seems to be enough. And that's what I want to recall now, because that sort of suggests that the diffeological approach is actually quite useful, even though it seems to be rather weak and poor structure if you first learn about it. Okay, so here's a kind of not finite dimensional group with still an interesting geometric structure that you can associate to any groupoid, any Lie groupoid. So that G1 also G2 be a Lie groupoid. So a section is so smooth and smooth. Sigma to one of, let's say, the right endpoint map is called a bisection. So geometrically, if you can just as well view the graph of that as a section of the other map, but technically you would rather define it this way if the map that we call phi of sigma, which is you take the section that you project down with the other endpoint map. Like the way I drew it, this would be the target map. And that's number and it's a diffeomorphism. So that's the picture. In the bisection, and here's your sigma, and then so it's a section of this. So this direction should intersect this transversely. So here I already have to watch out that was wrong. Then I project it down. So if you take a little piece here, say like you take this, and you map it up here, and then you map it down there. You better map it to there. That's your phi sub sigma restricted to an open subset, and then this should be a diffeomorphism.
Should we read an as G theories?
Pardon me? Oh, sorry, yeah. Okay. Yes, that's the picture. The interesting thing now is that this is a group. This is what Sander wanted to talk about if we had 1 more hour, I think. Okay, so the bisections. Form a group. So what's the multiplication? You have a bisection tau and a bisection sigma, and what you do, if you evaluate on a point x, well, you first take tau and x, then you project wherever you are down with this phi map. So you project up and then down with L, and then you divide the other section there. So that's now tau x, sorry. Right, and now you can see this matches straws and target match, and they can be multiplied. So this multiplication here is the groupoid multiplication, and yeah, this looks tautological. So the unit element, the identity of the groupoid and inverse. So only for the inverse you need that phi is invariable. So x is so you take phi sigma inverse. Then you take the groupoid inverse. So with the structure, it's good. And yeah, this you can do. So it's this interesting. So let's look at the first basic example. The peer groupoid. G1 m cross m for manifold. And that's a relation. So what's a bisection? Well, it's a section of this one, let's say, right projection of m. So it maps the point m equal to the same point m. That's our information, and it maps. And the first component is some smooth map. And now, the bisection conditions, you project it then to this one. This is supposed to be diffeomorphism. So this just is a diffeomorphism. Okay? So the bisection group is okay. That's an interesting non-finite dimensional group. Ready? And you can, I mean, physics relevant, you typically what local symmetries are in physical theories. Fermat physics or local gauge transformations are of this type, are bisection group symmetries. So for a local gauge transformation, this would just be a group bundle, show you a group bundle, and a bisection, then it's just a section of that. So it's just a function, group valued functions on space-time. And you have combinations of this. Okay? This just to convince you that that's interesting. And now comes the comment for Francesco and some other people who work with pseudogroups here. So let this be a well, you can do the same thing locally. So local section, it's the local section. The sigma is now defined Q, and it has to, and if and it's about identify the sigma, which is now endpoint map after sigma, which is now a map from U to something else in G1, if this is a diffeomorphism onto its image. Okay, now that's really the picture I drew here was a local bisection. Take a local subset here and here, down, up, down again. And this is supposed to be diffeomorphism between this open subset and certain subset. And yes.
G0 instead of G1.
Thanks. Thank you for paying attention. Exactly. Thanks. And so something we could make something out of here, but that's another class of examples, is that the local bisections of a Lie groupoid form themselves a groupoid over the set of open subsets of G0, because you can compose them. Okay, so that's an interesting class. I mean, some people here in the audience have studied a special case. So if G is the pair groupoid, and the groupoid of local bisections it's just the groupoid of local diffeomorphisms. Okay. Local. And a subgroupoid of that with sheaf properties is what people call a pseudogroup. Subgroupoid the sheaf-like properties. Pseudogroup. Which you encounter early in your studies when you learn about integration of vector fields. This only exists locally, and what this means, like for the sort of composition and so on. Or you write a PhD thesis on this. So the two gentlemen used here use this a lot. Okay. Wiping time. Let's see. Okay, and out of these various examples I gave you, I can construct more interesting groupoids that are decidedly not finite dimensional, but still have the kind of intuitively realized that already they have a lot of geometric differentiable geometric structure underlying them, and they may be amenable to differential geometric constructions. So, for example, if you have a dissection group, it's attached to field theory, then this often acts on the space of fields, or the space of sections of smooth fiber bundle. Let's say Lorentz metrics on the manifold and the diffeomorphisms. So this would be the basic symmetry structure of general relativity. And then you may take an interesting quotients to get from these action groupoids to groupoids that are not action groupoids anymore. For example, now you choose a Cauchy surface. Okay. And now there's a subgroup that keeps the Cauchy surface fixed, the points fixed. That's the one that's still compatible with your initial value formulation. And that subgroup acts nicely on the Riemannian matrix, but it's not normal. So now you can take this reduction by that gives you a smaller groupoid. And if you construct the algebroid, then you see that magically this, or perhaps not magically, this has the brackets of this realizes the Poisson brackets of the Gauss-Kudazzi constraints. That means something to you. Okay. So interesting things you can do with these things. Okay. So all these examples are based on function spaces. And what we have in function spaces, even if we don't want to group them with the Fouché structure or Vienna structure, or we want to make constructions that would destroy the Fouché structure, one thing that typically survives, or maybe some relatively robust part of that smooth structure is, as also Alexander has mentioned, is the notion of smooth families. So in function spaces, natural here means, well, you can take it as natural as in category theory and natural, that would be true, but you can take it as natural as kind of obvious. The natural notion. Let's take perhaps, well, that's the basic model, but if you go to the diffeomorphism group, perhaps notion of smooth families given by smooth homotopies. So some smooth map that form and now if we have an additional condition like you want to say in the diffeomorphism group, okay, let's perhaps really take this as our guiding example. Such that the map so Q is some parameter space, so that's an open subset of some Rn. So that phi sub U some map that maps this morphism. Okay, and like if U is R, that's just a flaw generated by a vector field. So if R sub U is interval, then flaw generated by a vector field. That's this direction. You can get this vector field by differentiating. So Say it again. That's true. So okay, either you add autonomous, or I just what I want to do is that at t equals 0 to see the vector field there, and when we start with the identity. Okay, just want to differentiate. You're absolutely right. Okay. So let's say e.g. is R and this. Okay, then I don't need to spell out the conditions to be autonomous. So the vector field, when I get it, is by differentiation. So this is a map that maps M2. Let me first write it down. Actually, so how does this make sense? Well, it obviously uses some kind of kinematic definition of tangent vectors. So you could make sense of this, for example, on a chart, or you could say, well, I have a notion of sort of jets, paths. They need to be tangent to have the same jet. So, well, I don't need to explain this to you. So this is this as an element in TM. So okay, so this gives you the tangent space at the identity of the diffeomorphism group. How about the brackets? So for the brackets, you need additional structure. So for brackets, you need to be able to talk about some kind of commutator. So you need to place this vector field in some kind of space of operators where you have multiplication and subtraction. The way this is usually done. Yes?
I'm a bit lost with this flow example. So this flow normally does not map from all of M to N, right? So if you have a whole and translations, then it's only for some.
Yes. So this is, you're absolutely right.
So what's this by U then?
It's a local flow, if you want. Okay. It will be defined on a sort of nice enough subset to still define your vector field.
Yeah.
Okay. So this.
It's just new notation. It goes from M to M. So that's by U.
Let's say it's compact. This is the native correction, but to be correct, okay, let's assume it's compact. Okay, and for the Lie brackets, so what we usually do is we define the Lie derivative. So use an action. The diffeomorphisms done infinity functions and go back. And then we can differentiate this and define this to be the derivative. So this is the vector field, the flow generated by V. And okay, once we have this, we can do this for the group commutator. Let's say we have so V. That's my, doesn't matter. That's my S parameter. And then we differentiate it. 0. And what we get is, okay, here comes one of the most annoying things, I think, in basic differential geometry, minus the Lie bracket of these operators, the commutator bracket of these operators in F. So someone has decided that LV is by definition of the bracket on vector fields is a left action, but this is clearly right action on F, and this is where this minus sign comes, and it haunts us through everything. Like, how do you define Hamiltonian vector fields, Poisson brackets? And, you know, there's always some sign that needs to be corrected somewhere. I think this is the evil origin of that sign. Okay, so upshot. If you view this to be a legitimate construction of the Lie algebra of a big non-finite dimensional group, then the upshot is that the Lie algebra is, that's my potential vector fields in the algebra of this. And what you need is, well, you need a bit. You need some things. So you need, for example, that the action is, well, for the group locally effective, perhaps you work, but for this you need that the infinitesimal action is faithful. Okay, so that what you see here as acting as some function, you can view as a relation on the vector fields themselves. And then the thing that Sana would have liked to talk about is you can generalize this. So the algebra of the group of bisections of the Lie groupoid is it, well, there it's okay, goodness. I think there you don't have this. I'm confused. Okay, let's leave the sign question open at this point. Is the algebra of sections of the Lie algebra. Okay, so you can view the Lie theory for the groupoids and the algebroids also as a piece of the non-finite dimensional Lie theory for the bisection groups and the big algebras on the section spaces of the Lie algebra. Okay, good. So let me see. So this proposition, so you find it in early notes by Anne Weinstein, 90s perhaps, and so like in earnest worked out with all details. I think this result with additional statements about additional structure is, I think, due to Alexander and Christoph Walker paper from 2015. Okay, very good. So we haven't talked about diffeology yet. So what is the upshot? What do we take from all this? It seems that, which is kind of nice, that all we had to do in order to derive the algebra of this big group of diffeomorphisms was the notion of smooth paths or smooth families. That sounds nice. So it seems only paths, smooth families, to differentiate bisection groups, at least, say certain types. Types of say should say this like D groups. It's not really D groups. But then, as at second thought, we get this very uneasy feeling that there's, and we know, of course, from literature, that there's much more structure to them that we have secretly or unwittingly profited from, probably. And we just got lucky with this kind of construction that everything works out nicely. So on second thought, so have we used well, structure? Unknowingly, so here are a few things. So the smooth families have some sheaf-like properties. Okay. We can take some of the properties on a cover or on small subsets, for example, of their domain. So does our computation secretly rely on this? Good question. Then diff has a structure for a Frichet manifold. So the question is whether this guarantees that our Lie algebra object is a vector space. So does this guarantee, is this needed? Vector space for the Lie algebra. And the third is, and that's a longer list, but there's maybe three obvious important things. So we have used that this algebra has a faithful representation on some space that comes from the underlying smooth structure. This has a faithful M, and if it were like an infinitesimal object for a bisection group of a groupoid, then well, so what's the algebroid? It's different vector fields on G1 on the aerospace, aeromanifold, and they have a nice representation on the smooth functions on that. So have we used this? And so the answer I'm trying to give to you in this course is yes, no, no. Okay, and that's going to be what I want to convince you. So because this in the setting we're considering, this is actually going to be gone. This is really my theory. Also, if we need this, then we don't need a theory of diffeological groupoids. We can do everything. We don't need diffeology. What's the point? We're working in Frichet manifolds and just use this as a special, very special type of diffeology. So that is, there needs to be some knowledge for these questions for this to be like a theory of diffeological groupoids to be interesting and new. Okay. So off we go to part 2 of the course, which is diffeological spaces. And more precisely, I call this some differential yet to be defined logical spaces. So instead of giving you the definition of diffeological space, because I would just barely be able to write it down, and then you have forgotten it by next time, I'm telling you what's good and what's bad about diffeological space. I'm giving you a slightly philosophical outlook. So diffeological space is a category in which you can place manifolds faithfully that has a super nice as a category. And that's what people, I think, I mean, Peter Micho might make this more precise, but like at the very least, it has limits, co-limits, and exponential objects. But the category of diffeological space is much nicer than a long list of properties it has. And as such, it is a convenient setting in which all the constructions that may fail for this bad category of smooth manifolds work. But of course, there's a big price to be paid, and that is it's way too general. It contains topological spaces and sets and weird stuff like spaces with the spaghetti diffeology, if you've seen this, or crazy cardinality products of copies of R, which you can use to construct really weird things. And what is totally clear is that there cannot possibly be strong geometric statements about such a category, unless you have a subcategory with additional nice properties that guarantee you the things you need to do differential geometry. And that's exactly the point of these elastic diffeological spaces. So the question I was asked by my students and also asked myself, like when I gave a course on classical field theory, and then people pretend, like if you lead linear free, they pretend that there's a Cartan calculus on the space of fields, so on smooth sections of a fiber bundle, that works just the same way as it works, for finite dimensional manifolds. How do they know this? Okay, and I realized they don't. I mean, you can either add strong conditions of locality, and that you're really talking about the variation bicomplex on client jet bundles, or on sort of infinite jet bundles, sorry. Or this was just wishful thinking. So the question I've asked myself, is there a nice, big enough subcategory, category of diffeological spaces, also one that you can sort out with a practical condition that you can check in specific cases, and you have still interesting constructions that you can use to construct good examples in this category. So is there a subcategory that allows for a honest Cartan calculus? And well, I have to say what honest is, but Cartan calculus for me is a graded Lie algebra on the ring of Durham forms generated by the Durham differential as a degree 1 derivation, the Lie derivatives and the inner derivatives. And that's what you usually use to do your local calculations in differential geometry. And the answer is yes, and that's the elastic diffeological spaces. Conjecturally, I cannot fully prove this. This is the largest category that has this property, at least in a, let's say, natural way, meaning really largest, not maximal. It really contains all categories that you can come up with that have this property or contain this category of elastic diffeological spaces. And then I'm going to show you, maybe this is a little appetizer for you to bear with me, but this may be interesting. There's a result that I find really, really surprising, and it says the following. Every diffeological group is elastic in this sense. I still sort of a bit dubious about this, but the proof is clear. And this, in hindsight, tells us why, as long as you work with bisection groups and and diffeomorphism groups, these kind of things, never anything bad happened because they have this nice, that's for me, the nice structure they had that I didn't know of was this elasticity condition and the Cartan calculus. And that is more tricky for groupoids. So this is a bit a preview of why I'm putting you through in the next, in the next lecture, I will put on a very categorical hat to sort this out. And that's really necessary because there's a zoo of more or less ad hoc constructions or differently motivated constructions of, for example, tangent function and diffeological spaces. 5, 6, 7 of them, all inequivalent. And now you realize, okay, I really need a clever way of going about this to assemble this to a full Cartan calculus. And that's why I need the categorical approach. Also, I have a higher structure approach in mind, what I'm doing this for. And the promise is, so when people tell you this, okay, we have a classical geometric problem, we need to go to higher structures or to higher categories or some fancy stuff to solve this. And then they go there, and the problem is they never come back. So I don't know if you know people like that. So I promise that I will come back to very old and concrete problems, and this is really supposed to be a solution of something you hopefully care about as I am a non-category theory person, or as a geometer. Okay, thank you.
So are there any questions? Any offline questions? Are there online questions? I don't see that.
I think it maybe
No questions?
There is a question from Foyle. If he could unmute himself and ask it.
So where does the word elastic come from?
I'm going to explain this.
Oh, okay.
Essentially, it comes from, it's a geometric picture that tells you that, so on diffeological spaces, you don't have, it's not manifolds, also not diffeological manifolds, you just have the plots. So they're your surrogate for your charts. And then the plots, or the collection of plots is supposed to have a property that reminds you of being able to strip out infinitesimal directions to a plot. Right, so that's what it will say. Okay, that's very, very rough, but I will explain this in detail. But technically, the condition is very simply phrased in terms of some functors, but it means something geometrically, and that's what this is supposed to convey. Oh, sorry, I should stay in my frame.
Any other questions here, or online, or wherever?
Yes, I'm sorry, but can we postpone the physical question to the lunch? Because I'm sorry to tell you, but Vienna is waiting for us. So we should thank Christian again. Please.